Hello, good morning, everyone. So this recording is for T-beams, so it will be a short recording, but hopefully you will get everything from this. Uh, Now I am starting to share my screen and I'm just opening up uh, the file. Excuse me. Hello, good morning. Yes. Yes, so I just wanted to confirm today in building F, F for Frank, the water will be shut off from 1 p.m. to 7 p.m., right? 1 p.m. to 7 p.m. Okay, thank you. Okay. Okay, I'm sorry for the disturbance. Uh, so, okay, so we are on T-beams. Now, what is the relevance of T-beams? So, let's go through a few points. So, first thing is that uh, as compared to a rectangular section, okay, so in a rectangular concrete section, we know that concrete is not carrying any tension. Only the compression part is useful, and then the tension is all carried by the steel. So it makes sense that this shape, this T shape, where you get rid of all of this is better than the rectangular shape. Okay, so this thing is one point. Another point is that if for the same amount of concrete, uh, if I use the same volume of concrete, I can get a deeper T section. So I have a larger moment arm. I have a bigger moment of inertia, so smaller deflections. So there are several advantages. So here I just wanted to show the concrete has cracked up to this point. So anyway, this part of the concrete is not useful. Okay, so I was just stressing on that point. Okay, the other relevance is that most of the reinforced concrete construction is laid monolithically. So that means after the rebar cages are set up and the concrete is poured, so the beam and slab, they are all poured together. Okay, so it is not, uh, sometimes the beams are precast, but a lot of times they are all poured as one monolithic structure. So uh, therefore the beam, it acts as a T-beam. So if you look at this floor, so there is a load on the floor. Now this beam, if you consider the if you consider a spacing between uh, these beams that you see here, then each of this each of these acts as a T-beam. Okay, so if I were to only consider this rectangular part, then my analysis is very uneconomical and not even correct. So it will act as a T-beam. Okay. Similarly, in a most common box frame, I just wanted to show how will it act. So you can see the beams here. So if you take the cross section, so that is a T section. Okay. So they act as T-beams. Okay, so now here there is one concept in T-beams, that is shear lag. So let me quickly explain this in a qualitative sense. So if I remember, when you just study the classical beam theory, how does the stress vary? This is the cross section of the beam. How does the stress vary across the cross section? So you have a linear variation. So if your beam is sagging, then you have compression at the top and tension at the bottom, right? So if I am at a certain height above the neutral axis, then I will have a certain stress distribution. So this is what we learn, right? That is true. But in the case where you have a T-beam with a very long flange, let's say like that, if the flange is very, very long as compared to the web, we can exaggerate it even more. Something like that. And if you load this beam, the stress distribution in this flange, if you look at the stress distribution across the width of this flange, it is not going to be uniform. Rather, it will be something like that. Like that. So why is it like that? So this is because of a phenomenon called shear lag. That means towards the center part of the beam, the normal stresses due to bending are much higher and the ends of the beam do not contribute as much. So if you remember that if I take this T section, if I make two cuts, if I make two cuts here and here, and if I look at this area, now this area is carrying shear, right? This is the one transferring the shear to the ends. So, but there is a lag here, uh, and if you just imagine this, the one way to imagine it, you have a long set of beams. You have a long continuous set of T beams like that. Okay. Now, if this one is very far away from these two are far away from this beam, then you can imagine just an intuitive way to imagine that this stiffness is much higher. If you distribute the load in the ratio of the stiffnesses, it is a loose way to imagine. Then most of the stresses will go to the stiffer part. So if you think in that way, you can justify that uh, this kind of distribution. Okay. But the actual reason is quite complicated. So we don't go into that right now. But it has been verified by both finite element analysis as well as experiment. So this is not, this is well studied. So what does the code uh, prescribe? So the code says that if you have a T-beam, okay, so flange location, there are two types given, each side of web, one side of web. So that means one side of web is a L beam like this. So if you take the end of the floor span, you will see a L beam, right? So something like at this end, something like at this end, you see a L beam, right? Like that. Uh, so for a L beam, you will follow this, and for T beam, you will follow this. Okay. So all of these values that you see here, those should be evaluated for the overhanging part of the flange. So if you see that this is the T-beam, this is the T-beam, then these prescriptions, they are for the overhanging part of the flange. That means that part which extends over and out of the web. Okay. So least of 8h. H is the uh, height of the flange. SW by 2. SW, what is SW? SW is if you have beams like this, SW is the clear spacing between these beams. Clear spacing, that is SW. And Ln, what is Ln? Ln is the clear span. That means if your beam is sitting between supports, so let's say uh, if I look at it from here, let's say here is a column and here is your floor span and here is your beam, here is your beam, here is the next column. So your clear span is from here to here, okay? So that is Ln, that is Ln. So ln over 8. So you need to take least of all these to get the effective flange width. So what is this? Sorry, I didn't explain earlier. So what is this effective flange width concept? We said that the stress is varying like that, right? It is not uniform, but we can take this as equivalent to, now I want to take a uniform stress instead of this variable stress. But to account for that, I will reduce the flange width. So I hope you got what I'm saying. So I'm taking a uniform stress now, and the total force produced by this uniform stress is the same as the total force produced by this variable stress. So in order to have that, I should reduce the flange width from what it was originally. So that is why the code prescribes these criteria. Now let's go to the design steps. I will explain it using pictures. It's very simple, the design and analysis of T-beam. So please listen carefully. Here is your T-beam. Now, your first step, of course, you will obtain your MU design moments from the design load. So that is there. Then after that, first step is to find the effective flange width. Okay. So BF from the using the code limit, you will get the effective flange width BF. Okay. So once you have that, note that there are two of them. So if you have isolated non-pre-stressed T-beam, that is, it is not part of a floor span, but it's just one T-beam. So if it is like that, your the effective flange width should be less than or equal to 4 times the web width. Okay. Okay. Uh, and there is another criterion too. The flange thickness must be greater than or equal to half of the web width. Okay. Okay. So if this is your T-beam, then you, okay, first thing is you need to write your equilibrium equation. For that, we in the T-beam, we don't know exactly where is the neutral axis. Supposing the neutral, or sorry, not neutral axis, we don't know exactly what is the depth of the compression block. That means A, depth of compression block A. We don't know exactly where it is beforehand. So supposing the compression block is within the flange there, okay? If our compression block is within the flange there, then this we can treat it as a rectangular beam, which is like this. So whose width is this width df, and whose depth is effective depth is same as the T beam. Okay. So we can, if the depth of the compression block A is within the flange height HF, so that means A is less than HF. If this is the case, we can treat it like a rectangular beam, and all the analysis is just like a rectangular beam. Okay, this case is simple. Now, if our if our compression block is beyond the flange, so that means A is greater than HF, so then you will divide into two parts, okay, this thing. So for that, first let's find where is A. Okay, how do you find A? So there is by research, by experimentation, it has been found that we can still use the compression block uniform stress 0.85 FC prime. This is the stress, even though we are looking at a T beam, even though it's not a rectangular beam, still the 0.85 FC prime uniform stress within this block, this assumption is still okay. Okay, so so what we do here is, let's say this is A, this is the depth of the compression block. Now I will write the total stress in this. Okay, how do I write? So let's write as two parts. Okay, total force in the compression block is, I will write as two parts. Okay, this is one part, this red part, and then these two blue, this and this is the second part. Okay, so for the blue I have 0.85 FC prime. What is the width? So BF is the total flange width, and BW, this is the web width. So therefore I have 0.85 FC prime BF minus BW. So that is the width. Okay, and what is the depth? Depth is HF, depth of the flange. Now how about the red part? Red part, I have 0.85 FC prime. Width is BW and depth is A, right? And this whole thing must be equal to AS times F1. Okay? So this is clear. It's just I'm writing C equal to T. Now, just like the doubly reinforced beam, it is convenient to split this right-hand side into two parts. So I'm writing left hand side is still same. Left hand side is exactly same. 0.85 FC prime BF minus BW HF. And this part is also same. 0.85 FC prime BW A. Okay. This part I break up into two. That is, I break up into ASF FY and AS minus ASF F1 in between plus. So I'm saying that this part I put exactly equal to this, and this part I put exactly equal to this. Again, just like the doubly reinforced beam, it is for convenience to make the calculations easier. We do this. We don't really need to do. We can do the whole thing as one. Even in doubly reinforced, we can just analyze the whole thing as one beam. We don't need to break up like this, but if you do, it makes our job easier. Why easier? Because now you can write, let's go back, let me just grab that. Okay, so now if I write the moment capacity, what is the nominal moment capacity? Now each of these have two lever arms, right? What is the lever arm for that red part? For the red part, here is the center of compression T. Here is, let's call this T2. Okay, for C and T2, what is the lever arm? Lever arm is effective depth minus A by 2, right? The A is up to here. Okay. Okay. Now, for this one, what is the, where is the C? C is at the center, so here, and T1 is again here. So now it is, see, this one is higher than this, okay? This is higher than this one because this is the center of this one, not the red. Okay. So for this one, it is D minus HF by 2. So HF is the flange depth. Okay. So Mn we write as the sum of two parts. Mn is Mn1 plus Mn2, just like doubly reinforced beam. Mn1 is, how do we write? We can either write as C times, let me change, C1, okay, and this is C2, okay. So we can write as C1 times, oh, I'm sorry, the red is C2, red is C2, blue is C1, okay. Okay. So Mn1 is C1 times D minus HF by 2, and Mn2 is C2 times D minus A by 2. Of course, we can also write as T1 times D minus HF by 2. We can also write as T2 times D minus HF by 2. Okay. And what is the total nominal moment capacity? Sum of these two, that is Mn. Okay. So this is how we do the analysis. So analysis is when we are already given the cross-section reinforcement, everything, and we want to find the nominal moment capacity. This is what we do. Now, how about design? Now for design, so if, okay, first thing is this depth, okay, this depth of the beam, let me explain to you something. This is T-beam, right? So in the, if we take a continuous span, so this is uh, like this, okay? So we take something like this. Now, this is the slab, this is the beam, right? So understood, this is T-beam. I hope it's clear. This is the web of the T-beam, and this is the slab which is forming the flanges of the T-beam, and these are the columns. So if you have something, okay, of course, it will not stop there. Like this. So here I had to change it a bit. This web you will see all the way through. So ln is from here to here. That is ln. Okay, clear. Okay, sorry that drawing error. Okay. So if you are like this, now how will you have your moments? You will have negative moments here and positive moments here, right? If I draw bending moment diagram, it's going to look something like that. Of course, how much is this, and this? That will depend on the end condition. So maximum, it can be WL square by 12 for fixed. And as you are less fixed and less fixed, it will start, the bending moment diagram will start moving. Okay, so you will have something like that. That means at the ends, you have negative moment. So for those, the steel should be there, okay? And this is this part of the beam is carrying the compression, right? So this usually this web depth or the total effective depth of the beam is decided by the negative moment regions, okay? So it is already known, this effective depth is already known, and the web width is also already known. So usually in the design problem, the only thing we are left to do is find how much is the steel needed. Okay. How do we do that? Again, the design procedure is somewhat similar to doubly reinforced beam. I have design moment MU. Okay. Now what I do is how much is the nominal moment capacity I can get from my flanges. So I will take the flanges and I will calculate what is Mn1. So for Mn1, see, I don't need to know how much steel is there and all of that, because Mn1 is, what is Mn1? Mn1 is equal to C1 times D minus HF by 2. And now HF is the flange thickness. Now flange thickness is also already known usually, because that is the depth of the floor slab and that is dictated by serviceability condition. That means floor slab should have certain max, it should be, the deflection should be limited to certain value. So the thickness is usually dictated by that criterion. Okay. So those are all known in the design problem of T-beam, in the design problem of T-beam for positive moment. So we are only needed to find the reinforcement. So C1 times D minus HF by 2, this is Mn1. What is C1? 0.85 FC prime BF minus BW. This is effective flange width BF. BF minus effective total flange width. Okay, it is. I will, when we solve the problem, that will be clear. Okay, BF minus BW. So all of the compression in this area. Okay, times HF. Okay, this is C1 times D minus HF by 2. So we, everything is known here. So we know how much Mn1 we can get out of this T-beam. So how much is the additional capacity we need? That is Mn2. That is Mu by phi minus Mn1, just like the doubly reinforcement. So now we know Mn2, right? So now, okay, now this procedure I'm showing is slightly different than the textbook procedure, but I think it is maybe easier. Okay, okay, it's up to you. I will show you both. Okay, mu by phi minus mn1, that is mn2. So now you know how much is mn2, but what we don't know is where is this where is the uh, depth of the compression block A. Okay, somewhere within this web. Okay, sorry, before we start, I forgot to mention one point. Okay, forgot to mention in the design itself. I forgot to mention one thing. What is that? So the first thing you will calculate in the design is like this. Okay, you will take you will take the maximum possible Mn as a when it acts as a rectangular beam. Okay, so that means what is the maximum nominal moment capacity I can get when this beam is still acting as a rectangular beam. That means the depth of the compression block is exactly equal to the flange height. Okay, so uh, this is when the beam is this is the maximum depth of the compression block that you can have, and the beam is still treated as rectangular beam, right? So how much will you get from here? So this Mn value will be 0.85 Fc prime. A is just HF, B is just BF, okay, the full BF. This is okay, this is the times D minus HF by 2. This is Mn, okay. So if Mu by phi is less than this Mn value, then there is no need for T-beam design, and just design as a rectangular beam with BF and D. So that means BF is the width of the rectangular beam and D is the effective depth. Okay. I hope you understood, because anyway, all this is not there. So this is just equivalent to a rectangular beam with width BF and effective depth D. Okay. Okay. So what now the next one is, supposing this moment capacity is not enough, then we need to design a T-beam. So that's what I was directly starting to show, design a T-beam. How to do that? So that's where you will first calculate Mn1 using the stress only in this overhanging flange. Okay, only that compression. So that can provide Mn1. Now the remaining Mn2 is mu by phi minus Mn1. Okay, so that we have to get from here, from this part. Now this is A, right? The depth of this compression block. Okay. Now A will also be used to calculate depth of the neutral axis. Okay. So for the overall beam also, this A is valid. If you have any doubt, I will explain this later. That just comes if you look at the overall equation. This A that you have, it is the true A. Okay. Okay. That means this A can be used to calculate the neutral axis. C. So Mn2 is this. What is Mn2? Like we wrote earlier, Mn2 is C2 times D minus A over 2 this time, right? A over, this time lever arm is D minus A over 2 for the red block. Okay. So what is C2 here? C2 is again 0.85 Fc prime. Now A is this A, neutral axis. Now width is only BW. Okay. Okay. 0.85 Fc prime A times BW times D minus A by 2. This is Mn2. Okay. Now here, what is the unknown? Only A. We know Mn2. A is the unknown. Okay. So we solve this quadratic for A. Okay. Now you got the A value. Then you also got C value. C is A by beta 1, right? You got A value, you got C value. Now what do? You will calculate AS. How to calculate AS? So first equate C1 to AS1 Fy. We already know what is C1, right? So find ASF. ASF Fy. Then take C2 or yeah, that's one. Take C2. C2 is AS minus ASF. Okay. We already know C2 also, because now we know A. So we know C1, we know C2. Now we know ASF, we know AS minus ASF. So what is the total area of steel? ASF plus AS minus ASF. Okay. Okay. So the rest is as you might expect. Now this is the only one I'm suggesting. This is the only part different from the textbook. We don't, in the textbook, they are using a trial and error procedure to find A, but we don't need, we can just solve this quadratic. Okay. Okay. So we have ASF, or we have the total area of steel. Now we need to check what is phi value, right? Now keep in mind, usually for T-beam, phi value will almost always be 0.9. Why? Because we have a big flange, right? and we have a deep web. This is the shape, right? Because of this, your neutral axis C will always be quite high than the bottom of the beam. So imagine now this is 0.003 and your neutral axis is always quite high. So your steel strain, your epsilon T in the bottommost layer will almost always be more than 0.005. But we need to confirm it. Then we got phi value. Okay. Then uh, then now you provide your steel. Okay. Then provide uh, as per AS. Okay. So look up in the table and provide the necessary amount of steel. Now we need to do the analysis part again. Check that PMN is greater than. Now for the analysis, uh, just now I showed you how to do the analysis. You need to again break it up into two parts, C1 and C2, and calculate MN1, MN2, and then P times MN1 plus MN2, which is MN should be greater than MN. Okay, this is the check finally. Okay, hopefully the procedures are clear. Now we will do one analysis problem, one design problem. Okay, so let's do this analysis problem. We have an isolated T-beam. Actually, I already did this on paper, so I will show you that instead of doing again. If any doubt, then I will, today you can ask any questions. Okay, so let's just go through over there. Okay, so here is our beam. There is 28 inches. This is our this is isolated T beam. Okay, 28 inches, and 6 inches is the flange depth, and effective depth is 26 inches. Okay, let's check the web width is 10 inches. So now we check here the code recommendation for isolated T-beam shall have flange thickness greater than or equal to half of web width. Okay, so what is the web width? 10. Half of web width is 5 inches. So flange thickness is 6 inches greater than 5. So we are okay there. Effective flange width less than or equal to 4 times web width. Okay, so web width is 10 inches. 4 times web width is 40. So effective flange width is less than that. Okay. So how do we analyze this beam? Now we are in the isolated T-beam, our effective flange width is already 28 inches. We don't need to check. There is no SW and all that because there is only one beam here. Okay. Now, first thing, as you remember, uh, if the depth of the compression block is within the flange, it is very easy. Just analyze as rectangular beam. If it is below the flange, then you need to do T-beam analysis. So let's check that first. So how do we check? Determine whether the depth of compression block is greater than flange height or less than flange height. So first we assume less than flange height. Okay. Then what will happen? AS times Fy will be 0.85 Fc prime times A times. Now it is BF, right? It is the compression block is totally inside the flange. So just A times BF. Okay. So what is the AS? You have 6 number 10. So if you look up, if you look 6 number 10, 1.27 times 6 is 7.62, okay, square inch. So now you will get, you solve for your A comes to 6.4 inch. So that means we cannot treat it as a rectangular beam. So we have to go for T-beam analysis, okay, go for T-beam analysis. Now we need to determine, as I said, we break it up into two parts. So one part is this and this. This is the first compression block. Second compression block is this. Okay. So now what do we do now? ASF times, okay, Fy is 0.85 Fc prime HF BF minus BW, right? So B of flange minus B of web. So that is the times the HF. HF is 6 inches. That means I'm just saying, what I'm saying here is just this blue area. This, what is the value of this blue area? BF minus BW times HF. That is the blue area, right? So that times 0.85 Fc prime, that is the C. What is T? ASF T1 is ASF times F1. So ASF you can calculate as 4.59 square inch. Now AS minus ASF is of course whatever is remaining. So 7.62 minus 4.59, that is 3.03. This is AS minus ASF. Okay. Now what is the A for web? 0.85 Fc prime A time. Now just BW for the web, that is AS minus ASF times F. Now we know this value, so we got A. Okay. Now we determine MNF for MN1. MN1 is ASF Fy times what is the lever arm for the blue part. Remember we said lever arm for blue part is center of this to the effective depth. So 26 minus 3. Okay. 23. 26 minus 6 by 2. Okay. So we got MN1. Then what is MN2 or MNW? So AS minus ASF Fy times, or you can also write C. Here I wrote T2. You can also write C2. That's fine. This is C1. Okay. Now this is MN2. If you remember for MN2, what is the lever arm? Lever arm is D minus, from here, center of this to D. So D minus A by 2. So we have calculated A already. So we got Mn2. So total Mn is Mn1 plus Mn2. We got it. Okay. Now what is the, we need to confirm the phi value. So our, what is the neutral axis? So our 7.13 was A. A value was 7.13 inch. And in this problem, the concrete is 3000 psi. So therefore beta 1 is 0.85. So neutral axis depth is 8.39. So you have the D on the other side 17.61. D 26 minus this. Then here you will get much more than 0.005. So phi 0.9 is fine. So you will, all, like I mentioned earlier, always, almost always in T-beams, you will get phi value 0.9. Okay. This part you can ignore. I confirmed, did some other confirmation and something. Okay. So this is our nominal moment capacity we have found. And design moment capacity will be 3 times Mn So 0.9 times this one. So that is our answer. That's how we find the moment capacity. That is the analysis problem. Okay. Okay. Now I will mention one more thing. Let's go back to this. So we said that to analyze the T-beam, we are breaking it up like plus this, right? Okay, this is not the only way to break it up. You can even do this is equal to only this part and some steel plus whatever is below, right? So this part, that's fine too. But what is easiest way for computation is to break it up like that. This will also work. Okay, so just to tell you that the fundamental equations are C equal to T and moment is C or T times lever arm. Okay, the rest is just for computational convenience. You need not follow exactly that way of superposition. You can do whatever you want. Okay, so that is the way we tackle the analysis problem. Now, if we want to design, want to go for design. Okay, let's look at the design problem. So we are given, this is our floor span. So let's write down what is our code recommendation. Let's copy paste it and that will be easier. Because our first step is to find the effective flange width. Okay. So like I said, the effective D, effective depth, the web width, those are determined by the negative moment part, which was designed as a rectangular beam. Okay, so those are already determined. Now, positive moment part is a T-beam. Okay. Now, what is H? H is 3. So 8 times 3, 24 inches. SW by 2. SW is clear span. 47 minus 11, so 36 by 2, 18. SW by 2 is 18. Ln by 8. Ln clear span is 24 feet. 24 times 12 inches by 8, which is 36. 36 inches. So least is 18 inches. So SW by 2. Okay. So what is our effective beam? You have 11-inch width here. And then on each side you have 18, 18. So that means it is just 36 plus 11, 47. So it comes out same as center to center. Okay. Okay. In this case, because they are not so far away, center to center is the governing case. If they are very far, then it will be something else. Okay. Okay. Now let's see how to do. Okay. First, I calculated the effective flange width. Then what is the next step? As we said, what is our design moment? Okay. Design moment was given to be 6,400 inch. So we have to design for this much positive moment. How to do that? So first calculate Mn1, like I said. So Mn1 is what is given by Okay. Before we go there, before we go there, I think I have not written down. Before we go there, check whether we can design as rectangular beam. Okay, check if we can design as rectangular beam. So what is the maximum MN you can get it? You can get if you design if while still keeping it as a rectangular beam. That means your compression block should be exactly there, right? So maximum MN is 0.85 FC prime DF, which is 47 inches, times HF, which is the flange depth, times D minus HF by 2. So you have 0.85, FC prime is 3 KSI. In this problem, DF is 47, HF is 3 inches, yeah, 3 inches, D is 20, 20 minus HF 3 by 2. Okay, so this is my maximum MN. Let me calculate that. 66 inch. Okay, so PMN is 0.9 times this, 5986.5 inch, but this is less than mu required, which is 6400. Okay, so we cannot design it as a rectangular beam. We need to design a T-beam. So we need to go for T-beam design. So we get MN1. MN1, as I explained earlier, MN1 is only from this part, the overhanging flange part. So this block, those give MN1. So 0.85 FC prime, and the area is HF times BF minus BW. What is the lever arm? D minus HF by 2. So if you do all that, we get 5094.9 inch cubes. Now Mn2 required is mu by phi minus Mn1, which is this 6400 over 0.9. Like I said, always phi will be 0.9. We will check in the end. Minus 5094.9. So 2016.21 inch cubes. Okay. Okay. Then so we know the Mn2 value. Now you solve for this quadratic, because what is C2? C2 is 0.85 FC prime A times BW. So that is the C2 is from here. Okay. So what is A? We don't know. BW is 11, web width 20 minus A by 2. So we solve for A by quadratic. We will get A is 3.99 inches. Now that we know A, calculate what is ASF. Okay, so and AS minus ASF. So 0.85. This is for the blue part. So ASF comes out to 4.59. Now for the red part, A times BW, AS minus ASF required. So that comes to 1. So total AS required is so much. Okay, so we can look up how much steel then we need to see whether it usually in T-beam it cannot fit in one layer. So usually we need to provide two layers. Remember, we went through all the rebar spacing requirements. We need to check make sure we are over the minimum spacing, and the maximum spacing usually we will be fine. Okay, so put in most likely two layers, and then we redo the analysis. Make sure Phi-Mn is greater than Nv. Okay, so this is the uh, T-beam, very quick explanation how to do analysis and design of T-beam. And I will upload this to YouTube in a few minutes. Okay, thank you and see you in the class.